Hello students. So up until previous class we learnt about a series solution. That means when you are looking for a solution around a certain point, then how you can write it in terms of a series expansion, right? And in the similar context we also defined regular point, then singular points, singular points, ordinary points, and these two terminologies. Then we also learned how to write down the solution when you have a singular point, right? So for second order ordinary differential equation, mostly we are concerned with these type of topics, and but of course you can define ordinary points and singular points for an nth order ODE as well. Now towards the similar lines of discussion, we will move towards very special type of differential equations, which are somewhat important, or to be precise, very important in a way, in the theory of ordinary differential equation, because they give rise to something called orthogonal functions, and orthogonal functions are also used in applied mathematics quite often. So we will mostly be concerned with two types of differential equations. So this lecture and the next lecture I will be talking about Bessel's function and Legendre polynomials, right? They are actually they actually come from second order ordinary differential equation. So to talk about it, let me just show you how does the Bessel's differential equation looks like. So they are called as special functions, and amongst that we are first going to look into Bessel's function, which actually comes from Bessel's differential equation, right? So how does it look like? So the standard form of Bessel's equation, equation or Bessel's differential equation, doesn't matter. Bessel's equation is, we can write x square d square y by dx square, or y double dash, whatever you would like to use, x dy dx plus x square minus of n square y equals to 0, where n is a non-negative real number, non-negative, that means it can be 0 also, non-negative real number. We can call this as equation number 1, right? So from here it is very evident that x equals to 0 is the singular point. So we can see clearly that x equals to 0 is a regular singular point. We have already seen the definition, regular singular point of equation 1, right? So the general solution will be obtained by a Frobenius method. So the general solution can be obtained by Frobenius method at x equals to 0, when n is not an integer. So this can be obtained by Frobenius method at x equals to 0 when n is not an integer, and we can write the general solution the general solution as obtained by Frobenius method at x equals to 0 when is not an integer is, so that we have a good continuation of this sentence, yx equals to a y1 plus b y2, where a and b are constants, where a and b are constants. So now this is a good statement, constants. This is equation number 2, right? So y1 can be written as y1x equals to x to the power n. If we use the Frobenius method, then it will be x to the power n 1 minus x square by 2 square n plus 1 plus x to the power 4 by 2 to the power 4 factorial 2 n plus 1, then n plus 2 plus dot dot and so on. Let us call it as equation number 3, and y2x can be obtained as x to the power minus of n 1 minus x square by 2 square 1 minus n plus x to the power 4 by 2 to the power 4 factorial 2 1 minus n and 2 minus n plus dot dot and so on. This is equation number 4. So, the equation 3 we will simplify, we multiply equation 3 by 1 by 2 to the power n gamma n plus 1. Gamma is our usual gamma function. So, from this beta and gamma function, that is the convergence of the improper integral, you must have known this gamma n plus 1. So, it has a particular form 0 to infinity x to the power n minus 1 e to the power minus of x dx. So, that is the same gamma function that we are using here. So, 1 by 2 to the power n gamma n plus 1 and denote the function by, what do we denote it by? Jn, that is our Jn x will become summation r running from 0 to n minus 1 to the power r divided by factorial r gamma n plus r plus 1 x by 2 to the power n plus 2r, and this is, that is this, and let us call this as equation number 5. This Jnx is called the Bessel's function of first kind, Bessel's function of first kind of order n, right. And if n is not an integer, so if n be or n is not an integer, then the second solution is j of minus of n of x equals to summation r running from 0 to infinity minus 1 to the power r by factorial r gamma minus of n plus r plus 1 x to the power x by 2 to the power n minus of n plus 2r. Let us call this as equation number 6. This j minus of n x is denoted by this. This jn minus x and jn plus x will constitute the solution, when n is not an integer, and we can write y is equals to a1 jn x plus b1 j minus of n x, where a1 and b1 are constants, right. Okay, now when n is an integer, so this is the case when n is not an integer. Now when n is an integer, then defining gamma n is equals to gamma n plus 1 by n, but this is our usual formula, gamma n plus 1 equals to n into gamma n for all values of n. For all n, then we see that gamma 0 is actually tending to infinity, and gamma minus 1 is equals to gamma 0 by minus 1, which tends to minus of infinity. Similarly, gamma minus 2 will also tends to minus infinity, and so on, right. So 1 by also 1 by gamma 0 will tend to 0, and 1 by gamma of a negative integer will go to 0, right. So that for r running from 0, 1, 2, 3 up to n minus 1, 1 by gamma r minus n minus 1 will go to 0, and we have what do we have? J of minus of n x equals to summation r running from 0 to infinity minus 1 to the power r by factorial r gamma of r minus n minus 1 x by 2 to the power minus of n plus 2r. This can be further simplified, summation r running from n to infinity minus 1 to the power r by factorial r gamma r minus n minus 1 x by 2 to the power n minus of n plus 2r, because when r is running from 0 to n minus 1, all these gammas are tending to 0. So we can start from n. Okay, and putting r equals to s plus and putting r equals to s plus n, where s and n are integers, so that r is an integer, where s and n are integers, we get j minus of n x equals to summation s running from 0 to infinity minus 1 to the power s plus n divided by factorial s plus n gamma of s plus 1 x by 2 to the power n plus 2s, which can be further simplified, and it will be written as minus 1 to the power n summation s running from 0 to infinity minus 1 to the power s divided by factorial s and factorial s, then gamma of n plus s plus 1 x by 2 to the power n plus 2s, but this is our j n x. So we can write minus 1 to the power n j n x. So this shows that j minus of n, so this implies that j minus of n is not independent of j n of x, and hence a second linearly independent solution hence a second linearly independent solution is required. Linearly independent solution is required, right. So basically by this calculation what we are trying to show, so since we have two, since we have a second order ordinary differential equation, we need to have two linearly independent solutions, right. So, we wrote down the first one, when n is not an integer, we wrote down j n x and j minus of n x, right. Now, when n is an integer, then we are writing, we have j n x, then we are simplifying j minus of n, and we see that j minus of n is equals to minus 1 to the power n into j n x. That means j minus of n can be written as a linear combination of j n x, or it can be written as some alpha into j n x. So, this j minus of n is not a linearly independent solution as j n x, right. So, we need another or a separate linearly independent solution when n is an integer. So, then we are now going to find out another, let us say, I do not know, since we are calling first one as j n x, we need to find out the second one. We can call it as, we will see, I mean k n x or whatever, but we need another linearly independent solution which can be the solution of your Bessel's equation. So, we have the first one, we need the second one. Okay. So, let us move further. So, let us say the general solution, if n is an integer, if n is an integer, the roots of the indicial equation will differ by an integer, right, by an integer, and the solution will involve a logarithmic term, So, the general solution, the GS general solution is usually taken as y is equals to a j n x plus b y n x. Let us call it as the second independent solution as y n x. So, I think I lost the track of equation number, but maybe this is equation number 7. Okay. So, this is equation number 7, where j n x form is same and y n x. So, j n x is as above, where j n x is as above the way we have defined before, and y n x will be given by 1 by pi 2 gamma plus log of x by 2 j n x minus summation k running from 0 to n minus 1 n minus k minus 1 factorial x to the power minus of n plus 2k divided by factorial k 2 to the power minus of n plus 2k minus summation k running from 0 to infinity minus 1 to the power k x to the power n plus 2k divided by factorial k 2 to the power n plus 2k n plus k factorial phi of n plus k plus phi k bracket close, where gamma denotes the Euler's constant and phi 0 equals to 0 and phi k is equals to 1 plus 1 by 2 plus 1 by 3 plus dot dot up to 1 by k, where k is equals to 1, 2, 3 dot dot and so on. So, this y n x is given above, or is called the Bessel's function of second kind, of order n. of order n, and this is equivalent to we can write in terms of limit, equivalent to limit nu tends to n j nu x cos of nu pi minus of j minus of x divided by sine nu pi, j minus of nu x by sine of nu pi. So, for non-integer, so therefore, what we can say for non-integer, n, it is obvious that y and x being a linear combination, of Jn and j minus of n is linearly independent, of j and x. And in particular, if I take n equals to, let us say 0, if I take n equals to 0, that means Bessel's equation of degree or of order 0, then we will have x square y double dash plus x y dash plus x square y equals to 0. So, my j 0 x, that means Bessel's functions or Bessel's equation is given by this. So, Bessel's function of order 0 will be given by 1 minus x square by 2 square plus x to the power 4 by 2 to the power 2 square 4 square minus x to the power 6 by 2 square into 4 square into 6 square plus dot dot and so on, and j 0 x log of x plus summation n running from 1 to infinity minus 1 to the power n minus 1 x to the power 2n divided by 2 to the power 2n factorial n whole square into 1 by into 1 plus half plus 1 by 3 dot up to 1 by n. So, this is our y 0 x, right. So, for a Bessel's differential equation of order 0, we have Bessel function of first kind as j 0 x, which is given by this, and y 0 x is given by this, right. And from here we can also have something called modified. So, we can have modified Bessel's function, modified Bessel's equation. So, modified Bessel's equation is a little bit of this type: x square y double dash plus x y dash minus of x square plus n square into y equals to 0, and this is called as modified Bessel's equation, and its general solution can be written as general solution of, let us say 1, this is equation number 1 of 1 is equals to or comma y x equals to a j n x, or j n we have used. So, I n x plus b I minus of n x, right, where I n when n is not an integer, when n is not an integer, and a and b are constants, and I n x is defined as I to the power minus of n j n I x, where I is our usual imaginary number, and this is given by x to the power n by 2 to the power n gamma n plus 1 within bracket 1 plus x square by 2 2n plus 2 plus x to the power 4 by 2 into 4 2n plus 2 2n plus 4 dot dot and so on. So, this is our usual INX, and when n is an integer, and when n is an integer, when n is an integer, then the general solution is yx equals to a1 INX plus b1 knx, where a1 and b1 are constants, where a1 and b1 are constants, and knx is given by pi by 2 I to the power n plus 1 jn ix plus I yn of ix, where INX is called the modified Bessel's function of first kind of order n, and knx is called the modified Bessel's function of second kind of order n. Right. So, obviously, I mean, we spent the entire lecture on derivation of Bessel's function of order n of first kind and second kind. There is a whole lot of derivation that goes on. So, I wrote down basically the formulas that are concerned or that are related to basically our Bessel's differential equation of order n. These special functions are very much useful in our analysis of differential equations, and also the places where we need the orthogonal functions, right, especially when you are forming the basis for a certain function space and all that. So, this Bessel's functions are quite useful in several fields of applied mathematics, and here we just did the derivation in a way, but not in detail. We did write down the important formulas for the Bessel's differential equation. So, we'll in the next class we'll start with the Legendre polynomial or Legendre differential equation, and then from there we will derive the Legendre polynomial. And these are the two special functions that I wanted to talk to you about in this particular course, right. As far as the application is concerned, so there might be some examples in your assignments where you need to determine, let us say, a value of Bessel's function at a certain point or a value of the solution at a certain point. So, if you can identify that the given differential equation is of type Bessel's differential equation of certain order, then you can just substitute the value and you can determine your j nx at that particular point, then your y nx at that particular point, then you can write down this value of the solution at that particular point, right. So,